let's start with our practical session for the 5th week for the generative models. And we will also talk about generative models in a little bit more practical sense today. We will talk about using a variational autoencoder on a small dataset. But we will also focus on basically on the dataset side of the things. And I prepared some codes and some intro into how to scrape pages from the internet, basically. Okay. So all of the codes are already in our Git repo. There are two resources, the scraping the internet notebook and then variational autoencoder notebook. And so let's start with the first one. We will sort of be showing on this in this notebook something that you would probably be doing on your own PCs, but I still wanted to sort of make use of the virtual machine given by Google, and also sort of the way that I can share this this resulting notebook as well with you, and sort of everything is sort of in one place rather than me just writing commands on some command line and then you having to copy paste it somewhere. But basically, what we will be doing here is something that you probably would be doing later on your own PCs. So one thing to sort of note is that when we are using the Google Colab, we are connecting to some virtual machine somewhere, and that machine is running Linux, and usually has access to some GPU or none, depending on what we chose. I think we don't need GPU for this one, so it's okay. And so there are two ways of interacting with it. One is writing Python codes directly, and I guess that maybe is not even here in a lot of these commands. And we have seen that, right? So if you go with print hello, this is actually a script which is run by the Python implementation. Whereas if we preface anything that we write with an exclamation mark, sort of like ls, which is a command to list directories in the or the content of the directory that we are in, this is actually calling a command from the Linux machine. So rather than using the Python interface, we are calling the command line of the Linux machine. And so I think if you write this, then it should open up a Python, and then you are sort of writing the same here. But this is doing it really like, wow, it's even hiding this. Okay, let's see. Yeah. Okay, this is this thing that I'm writing a password, I guess. So yeah, you can do the same thing like here, and then it becomes, let's see, exit. So this is just to show that this is an execution of a Python code, which is something that we could do here as well, or execution of scripts. So accessing the command line could be done, or the files could be done something like this. So printing out the contents of some folder, or saying that I think we are in content or something, and then sample data. So this is like something that's already there loaded, and another way to show the files is through this menu here, and then you can sort of look at these in a slightly easier way. But like, yeah, in here you don't see the sizes necessarily. Here you can have some special commands to print out the sizes, the dates, and everything. So anyway, this is not really that important. I just wanted to sort of show you that there are differences between the commands that we are running this with. Okay, cool. Well, so what is this notebook? Well, there will be two demos of attempts to scrape the internet somehow, or get some images or data from the internet. As you sort of, I guess, already know, all of these models that we talked about are really data hungry. So when you scrape some data, you really need a lot of it. And so this means thousands. This might mean also like 3,000. This might be even something like 30,000 of images at various resolutions, which is quite a lot. And if you are downloading it by hand, it would not be feasible. you sort of need some scripts to help you out. And even at that moment, if you have those scripts, there might be some problems. So let's talk about the first one, and that is the Google image download. It is a repo coming from this source actually first, whereas this version is out of date somehow, and there is an error which makes it not really work well today or these days. So there is a fork from this repo which fixed some errors, and this one is working. And we are also looking at the at a branch with patch 1. So anyway, this is like a version of some code that someone uploaded somewhere. And we can directly access that patched code by telling it, let's go into branch patch 1 from this address. Okay, so we running this, we have cloned it into a directory, and then we go into the directory, we install it as a library, and then we go up again. Basically, this is what this means. So let's do this. This is something you could be basically doing on your own PCs as well. Python is relatively platform independent to some degree, so you would be able to use Git, and you would be able to use this pip install or Python setup installs, stuff like this. You could probably use it on your own PC as well. It could be a Linux, it could be a Mac, it could be a Windows machine. And then we can run this. Basically, we are running this script that we installed here. And it tells us that it's basically running, except we are not giving it the right keywords or the right arguments. So remember, we were using something like comma or exclamation mark ls to give a to run the command ls. So in this case, it's a exclamation mark Google image download, which is you would be using this without the exclamation mark. So there are all sorts of keywords that you would be adding into it, and they are basically here. So let's see. And all of these keywords allow us to somehow change the search that we are making and use this code to scrape images from that search. And let's see what does that actually mean. If we go to Google and look at, let's say, New York, because why not, and then go for images, these are a bunch of images that we sort of would like to maybe download. If we are making a dataset about New York, let's say that this is the images that we want to somehow scrape. If it was something else, then you would sort of change it here, and you could also sort of change the commands here. I think there are some special ways how to like write that I want to access a site of some sorts or something, right? Or I think there are some ways how to change the sizes of the image, change the color and stuff like this. Well, all of this is sort of filtering the results that we would be getting. And the same happens with these arguments that we can set here. So keywords is basically what we would be searching here. So the keyword New York, let's say. Something like color, size, exact size, aspect ratio. There might be some details about license as well, probably. That one is important, right? Yeah. Okay, usage rights, labeled for reuse. Something like this could be useful. And these are the commands that we would be adding to this code, right? So kill this from previous searches. I can sort of ask this script to run me a search with the keyword New York, limits it to, let's say, 30 for now, and this will search the same way as I did in the window here, get these images, and then directly start downloading them. And so this is a simple way how to sort of from search start getting images. And it downloads them into a folder called downloads / whatever the keyword that you had was. So let's print out all the files there. So in this case, we didn't have any errors actually, but in general, there can be some files that are not possible to be downloaded because they are on some strange websites, or I don't know, they are somehow controlled. So if you look at the files that we downloaded, we can see that there is quite like wild bunch of images. Some are obviously of higher resolution because they have larger sizes, and some are some really small images, something like thumbnails or something. And so you could probably go quite into a lot of depth by saying something like size, and I want the size of everything that's bigger than, let's say, this thing. Right, probably you might have to enclose this, I guess. And then for some reason we also would like to get all images that are, I don't know, red. And then you could repeat this command again, and then it would still download the same. It would download images into the same directory unless you change this, I think, right? Well, let's see. Let's downloads. I think it doesn't differentiate between the folders. So it was okay. Actually, it did. Okay, cool. So then let's see in this case, all of those images are, well, at least this size or something, right? Well, so this is just a demo of sort of showing you a really a nonsensical search for now, because we are just searching for some images from New York. But this is a introduction of how you would use this resource to sort of search for your own area of interest, and then I don't know. It should work in other languages as well. Dropcheek is a type of a beetle, and so if I'm collecting a data set of beetles, I am not sure if this will work at all, by the way. But yeah, actually, Mravenec is an ant, so this should work. This can also horribly fail, so I'm not sure what this will find. But you can sort of fine-tune your own searches to some other data sets and sort of try to acquire images from one particular type. Okay, so you can see that 12 of these images actually had some errors because we are trying to access some websites which are maybe sort of protected against this sort of scraping. But nevertheless, if we look at the this folder, we did get a folder full of beetle images, I think. Cool. Well, so obviously you would be running this on your PC, so you would be then you can access those folders and see what you downloaded. And doing it in here is slightly awkward, but if I run it like this, there is a script which will just open up all those files and load them, and then we can print them out with the name and the resolution. So in here you can sort of see that it's a wild bunch of all sorts of things, and then finally you can sort of print them out in a figure, which, yeah, so cool. If I'm accessing a data set, this is maybe useful. These probably would be useful. These. But maybe these images that are more or less like plots and stuff would be rubbish for me. So this is just sort of to denote that this type of search also will need a lot of later guidance over the data set. So let's see the results from the New York search. I think that might be slightly easier because that one is just images from the city, so there is less ambiguity in the search term. So let's see what that one goes with. Right, so you would get images that are more or less similar to something like what you could see on a postcard or something. And so this could be one data set that you're sort of collecting. Well, so this is one way how to download images. The another way is actually just like trying to find a dataset which already exists. So something like machine learning datasets, and then going one by one, and then sort of like trying to use either the canonical ones, so some large images which have a lot of them, but they are sort of relatively boring categories, I guess. Or you could start searching around museums. I think there was Collection open access. So I think there are some museums that will allow you to access, to look at some images of some resolution. So this could be some very specific data set here as well. And at that moment, you could sort of start searching by, I don't know, let's look at bones. And then you could start collecting datasets which are specialized, which are not coming from Google or some generic source, but from some other datasets which are more like fine-tuned. The problem here is that you would have to sort of scrape it yourself. I think there even might be some codes out there as well to scrape these datasets as well. But at some moment, if the web page is too strange and not used, which Bat Museum probably isn't actually. Some people already might have scraped this. But if there is a website which you are scraping, which is slightly weird, you might end up having to write all of that code yourself. So this sort of illustrates the possibilities and also the problems with collecting datasets from the Google search. I think one thing more to note is if I add a super large number, I think it will start yelling at me, so that I don't have installed Chrome driver, which is something you might have on your own PC, but maybe it needs some more setup. So at that moment, something like offset is handy because you are sort of offsetting by 100, so skipping the first 100 samples, but then getting the next 5 or something. And then this will sort of go around the it should go around the limitations of the of searching for just some images, or of being limited to like 100 images. Well, so this is one way sort of how to do this. Okay, so I guess I ended with the images on this site. If you care about other types of data than images, there is another sort of demo which is trying to show how to download images, how to download web pages as sort of text. So I was involved in a fake news generation project where we were sort of getting articles from some websites and then trying to fine-tune, sort of find categories of those articles, get a smaller data set from there, and then sort of train a model on those categories and sort of try to figure out if there are some types of news that are being misused in fake news more often, which is probably some political news and stuff like that. Well, and for that we had some sort of code to scrape articles from the from news pages, and for that we will again be using sort of two types of libraries, and these would be the newspaper 3K and a Google Search API. So I think this might be a little bit similar to the one we had before here with the images, but anyway, it works with this code, so it was easier to prepare. So let's wait for these to download. This one will be slightly more messier in terms of code because it was used. Okay, it was used specifically for like this one targeted thing to download articles from website from the internet. But you can sort of reconstruct this code a little bit and maybe edit it to start downloading some other type of data that you might want. Okay, so we are sort of still loading some libraries here. Then we will make a folder called articles, which we will use to download those articles into. And then let's say that we want to search for New York and New York City again. Okay, well, Google Search, this is using one of those libraries. We will query for 10 pages, get results worth of 10 pages of articles, and then process these links later. So let's see how fast this goes. So this is going one by one in queries, so we have just one query here, but we could have more in theory. And there is some processing of the links that we will get, and then we can print out those URLs and the results. So at this moment, we are sort of getting all of those articles that we got on some pages. The pages are sort of from various sources, so there could be TripAdvisor pages, there could be some Wikipedia pages, there could be some actual articles from news agencies as well, which was the stuff that we wanted when working on this project. So these would be the direct links themselves. And let's say I want to throw away some type, so let's see that maybe I don't like Wikipedia pages, so I can throw them out by this command. Actually, in this search there was nothing by Wikipedia, so let's throw away TripAdvisor links. Okay, that was one. Well, anyway, so we ended up with like some links which we can then later check again. But let's say that we New York update about Corona, lockdown, New York City, some news. Let's say that we want to focus on this 3 first, but in reality we would probably just run it for everything. And then we will run this slightly messy code, sorry for that. It's a code which works like a spider, which is sort of jumping one link by link. So it starts here, it downloads that article, this one, and at the same time it gets the links for other articles in the okay, it gets the other links from that site, which would be leading to other articles, and then it continues on those other articles as well. So it is like a spider sort of moving around the websites and sort of scraping everything. So if we run it, it is starting here. It knows that there are, I think, what does this mean? I think there are 100 links from this website, which means that it's saving articles from that website where it got. And I think at some moment it will also start using those articles as other resources to jump from. So it's basically going endlessly until it gets everything. Okay, it got into the second one. Okay, cool. Well, so I will actually stop it because this will run for a long time, and some of those articles might be a little bit messy. So there are two sort of things to note. One is we have to sort of stop it manually, at least in this demo, because I don't want to download too many articles. And at the same time, there will be a lot of junk when this code is done, because it was just jumping from website to website, so it can encounter anything which may or may not be relevant. So this is sort of similar to the way how we were searching with the image search. If you are just purely looking at the scraped Google Images data, there might be a lot of things coming from those terms. So it sort of illustrates that finding a nice dataset of any sort of type is actually quite difficult. So let's see. These are the scraped articles. They are saved in a JSON file. Let's find, I don't know, let's find like one of them. Something about food on plane, nice. So let's load this one up. And then we can load it, and then we can print it out, whatever we saved. And how we processed this was using the newspaper library, which also sort of tries to classify it. So this library tried to classify some keywords from this article. So this is something about windows, about planes. I guess it's not the best at this classification, but it's a sort of a helpful way how to sort of sort out through the data. And then we get the URL, the date where we of the article, the title, the authors, and the body of the text. And here we have the raw text of the article. Okay. Well, sometimes it happens that this text is too short because we maybe have downloaded a fake news story, which is sort of short and sort of maybe bombastic, and maybe there is one image and then one title and then nothing else. And so you sort of have to sort out through your data in any of these situations. But this is one way how to sort of collect datasets. Let's see how many we got here. yeah, you could then start analyzing it in terms of like how many you got, in terms of fine-tuning the categories that you used for search, and maybe eventually even manually going through some of them, which might be really labor-intensive, but maybe that's the way how to sort of the only way how to get sure that your dataset is actually quite nice. Well, so I am not sure if you will be able to use these codes in your project. I think I wanted to show you that these are the ways how to sort of start getting some data from the internet in a very raw way. So you can find datasets that already exist there, but this is a way how you can sort of create your own searches, create your own categories, create your own labels, and then sort of start plopping images into those labels and into those categories and creating datasets from that. Okay. Okay, so I think this is it for this demo. As it is right now, it's not that useful, I think. But if you search with larger searches and maybe over multiple times, you might get more data that is of sort of relevance. But this was just a sort of demo of the concept of scraping data from the internet. I guess last notes would be that there might be some domain-specific scrapers for something like Tumblr, for something like Twitter. I don't know. You might get some API calls and then some libraries that are working with those particular sources of data, and you can sort of try fine-tune your searches there. And if the website is too not known, sort of too bizarre, you might have to even write something on your own. But you can sort of start using these as a starting point. So the data that you got is very raw in some sense. Basically, it comes from all sorts of types, shapes, and everything. And the question really is that if you need to post-process it somehow, and the answer is yes. Basically, if just like the most obvious thing, if you look at the resolutions of the images that you got, they are sort of really non-standardized, and so some are like 10% of the resolution of some other images or something. And so you might have to sort of find the common denominator of all of these somehow. Maybe find like one single resolution that is smaller than all of these, or some fixed one, and then resize all of those images into the smaller resolution. Because a lot of the networks that we have been using, especially when you have a fully connected layer somewhere in those networks, at that moment they become they need a particular resolution at the input size. And so at that moment you would have to standardize all of your data into into one single resolution. What is also done is that there is some sort of normalization across all of the data. So you would probably want to fit it between 0 and 1. And ideally not even in between 0 and 1. You would want to find some averages and then sort of divide the data by the averages and everything. So you are sort of even fine-tuning it for that one specific dataset. But I guess that's a lot of technicalities. I think at some moment the more important part of post-processing your dataset is just to go through it and actually find images that are there. And especially when we were doing some automatic searches like these, you would have to really go one by one almost, or look at them in some like high-level resolutions like these to check if what you are searching for is actually working, and if you don't have some noise in your dataset, sort of, or something that you wouldn't want there, or some duplicates, or etc. etc. Right? You can sort of, I'm sort of just saying some of those problems, but there might be more and more issues coming in from this. So yeah, collecting a dataset is not an easy task. If you remember from the I'm not sure if it was mentioned in the AlexNet paper actually, but what they did was using a ImageNet dataset, and that dataset was unusually large in terms of images, but those images were were labeled and classified and sort of like sorted out by a bunch of internet users. So bunch of what was the name of it? Amazon Turks, which is an automated system where you can get money for classifying images. And so a bunch of people were classifying images over a lot of time, and that's how they sort of build those datasets. Sorry. So that is one way. I think I have seen a lot of datasets being collected by Amazon Turks, basically, but it's not the best one, obviously, because there might be all sorts of biases. There might be all sorts of reasons why the people are classifying those images by labels that might not be perfect, and so there's all sorts of problems lying in there as well. Okay, so I guess what I want to say with all of this is that getting datasets is relatively hard, and you should definitely try doing it, but there are all sorts of things you should and you will have to sort of consider while doing so. So, I don't have any slides prepared for this, but dataset augmentation, cool, let's use this resource. Dataset augmentation is a way how to sort of blow up your dataset, sort of make more samples from some limited amount of samples you have in your dataset. And the way they do this is basically applying some transformations for those images. And those transformations might be something like this. So translation, rotation, some shear edits. With medical data, what you can do is also some non-linear edits, so some sort of plastic, sort of not blurring, but like moving around of tissues. I think, let's see, medical data, maybe. Right, so with these tissues and stuff, what you might do is apply some sort of transforms which change them. Elastic transform. So sort of something like this, some distortion. I guess this is a good example because it will not really work because this is not something that you would like to see in real life. But this could work with some smaller images from tissues. Well, so the way why people augment their datasets is, or the reason why they do it is because this will blow up the amount of data in your dataset, and the training will get roughly better. You're sort of adding some fake images inside of it. There may come some problems from this because maybe you will start generating cats which are not the the type of cats you wanted. You might start generating just some parts of them. So you sort of have to make edits which make sense. I guess this might not make sense as well, right? So for some types of data, some types of augmentation edits might not really work. But that was a good question. Data augmentation is something that you can use to sort of blow up your dataset. So let's say you download 1,000 images by the methods that we talked about, and then you can augment the dataset for basically twice. Or yeah, like you can enlarge the, like with all of these edits, you can scale the amount of images quite rapidly. The question is really if there will be any if you are giving it enough new information. So if you overwhelm your network with a lot of duplicates of the same image which are slightly edited, it might also cause some problems. Right, let's have a short pause. After that pause, let's jump into the second notebook. We will work with variational autoencoder model, a relatively simple one and a relatively small one with a 28 by 28 pixel dataset. And hopefully we will be able to show some uses with, or like some interaction with variational autoencoder. Okay, so I wanted to address the last question, which was about license issues and sort of getting data from license sources. Well, it's a problematic question for sure, because there are techniques by which you can sort of, even though you train your model on some data set and then release the model on its own, and you sort of don't give anyone the data set that you trained it on, there are techniques that can sort of reconstruct the visual material from that model and somehow show what has been put into that model. Well, so one of those techniques is basically called Deep Dream, and without going into too much detail, it's something which can be illustrated by this. You work with existing model, and you use the weights inside that model to sort of change the any input image that you are trying to use with that model. And what happens over time is that you start getting shapes which would correspond to the images that the model is expecting to get. So in other way how to say this is that you will sort of start getting shapes from the training data set in that edited image. So for example here, the images that or the thing that this was trained on and the visualization that they are getting here right now is probably some buildings, some pagoda type shapes. And so this is a way how you can sort of extract some imagery from a trained model even though you don't have access to the original dataset. Well, this is not perfect for sure. This is like a bit messy and you cannot really reconstruct the images 100%, but the truth is that somewhere in the model this information is there already. So I think it's probably quite like a large question, which is still an open research question basically. If something that you train the model with, if it can be reconstructed from the model. So there are all sorts of privacy concerns there if you allow a model by Google to train on your images, which probably happens. Is it all right? Well, I don't know. If you train your own model on some copyrighted material somewhere, will you get into trouble? Well, you may, probably, even if you don't show the data set with this. Well, so how people even like approach this problem is that they collect data and images and sounds and whatever, which is in Creative Commons license type, different types. So something that is possible for reuse, and there are all sorts of types for. Oh no. I didn't check. Well, sorry. It automatically translates into the language that it shouldn't be in. Okay. Well, so Creative Commons are sort of like annotations for of works online that people can release their data under, and some of those types allow you to reuse the data and or collect it, use and remix it, right? So yeah, I guess this limits your search for the dataset even more, because you have to sort of find images which are licensed under some specific type. Some of this allows you to use the data if you are using a non-commercial product. Some of it, basically, you can use it wherever, even for commercial stuff. Well, and this extends to like music, songs. If you ever worked with YouTube and they're sort of uploading some music there, you probably also know that's part of the work, because the music can be identified and then the video might be pulled down or something, or marked as using some other types of data that has been licensed. So yeah. And so the problem is that even if you train your model on something that has been licensed, people can probably figure it out. Maybe not now, maybe later with additional research. Maybe they wouldn't care, but maybe it's morally not okay to do it anyway. So my stance on this, I guess, would be if you are trying to play around with an idea, you can go all the way. You can just scrape data from anywhere and just play around with that idea, try if it works on some types of data, if it's something that you will not release. And then sort of maybe if you are wanting to release that, you can sort of find the data set that would be okay in the sense of licensing as well. Yeah. Okay, so let's work with one of the models that we introduced in the slides in the presentation, and that would be an autoencoder model, and in this case a variational autoencoder model. So this notebook is sourced from various codes somewhere else. So I used a little bit of the data from the Keras repository and also for the ML4A, and mixed it into and sort of wrote a new model as well. So maybe mixed in some visualization from those codes. So this will be a lot of code that we will just run and then look at the results. Basically, it's using a lot of the libraries that we already saw. So Keras, for example, NumPy and Matplotlib for plotting. And then there are some sort of functions that are specific for the for this model, for the variational autoencoder. Okay, let's check that we have GPU. Okay, cool. And let's open up a dataset. So there are some the older sort of results in this Python notebook are results from the quick draw dataset. You can sort of run with that later as well. I think I will start with the MNIST dataset because that one is easier to sort of show and also faster to train. So we will load it up in the same way as we did in the previous lectures, and we can sort of look at the different samples. So we have data, which is 28 by 28 pixels. And it's a grayscale, so there is just one channel here. And this data represents 10 classes. So basically from handwritten digits from 0 to 9. And as you can see, there is 60,000 images here. So let's say that something like this. Ooh. Oh, test, right. I'm looking at tested dataset. So that one has a 10,000 images. Okay, cool. So we could be using some other dataset by called QuickDraw, which is a small collected sort of dataset used for creative practice. So some shapes drawn like this. This one is the full dataset has a lot of categories. I think there is a smaller version which has just 10 categories. We can plug in that and sort of reuse it the same way as we would the MNIST that we will be working with now. But I will start with MNIST and then see if we have some time to swap into the quick draw. Okay, well, in today's practical session there is a lot of code which we will just rerun. This part of the code is us building the model. So if you remember, we are sort of using the same building blocks that we used in our previous classes. So some stuff, when we were working with the convolutional neural network, we were building a network from convolutions. And actually previously when we were building the network from fully connected layers and stuff. So in here, we are sort of following the theoretical explanation that was there in the class, but actually writing it in code. So what we want to write is a network of a encoder type, which will go from an image into some latent representation, and then another network, which would go from that representation into an image reconstruction. So we are sort of writing two networks, one here, and then also build all of that into one sort of block that we can then train together. Okay, well, so I will explain a little bit what's happening here, but I will not probably go into too much depth. We have an input layer, which is basically just taking in the input, and then a combination of convolution and max pooling, so convolution and downsampling layers. And as you can see, I have been playing around with the code and sort of changing, adding some, deleting some. The exact amount of layers that you choose is sort of arbitrary. If you add more, the size of the model is larger, so it can learn more complicated datasets, but it will fail on less complicated datasets. So I was sort of playing around, adding layers, removing them, and seeing what it does. So this is why this is commented. Other than that, we are sort of working with two types of layers: convolutions, max pooling, convolution, max pooling, again convolution, again max pooling. And at this moment, I will show that again in a summary of the model. We flatten that vector or that information into a vector. There is some magic tricks with batch normalization, but it wouldn't really be necessary, honestly. And then there are some fully connected layers, which means that everything from here, from this X flattened vector, is then being reconnected with a fully connected layer. Okay, so this Z-mean and log-var are things that are specific for the variational autoencoder, so that one has some probabilistic theories behind them. And yeah, basically the Z, the latent variable Z, is sampled according to some distribution of a Gaussian shape. So there are some tricks happening here as well, which we don't have to really go into that much. Okay, and at this moment where we have the Z, which is somehow reconstructed from all of those things, from inputs, convolutions, and max poolings, we have an encoder model. So that one is built from an input and then eventually the Z output, and then some tricks for the variational autoencoder. So if I were to comment this here, we can create an encoder model and then just print out the summary of this model. Okay, so this all worked, and if we print out the summary of this model, so this is something that we have been using with previous models as well. We basically have the same thing that we were writing here in code. We have it here as a sort of just summary of that. So we had the input layer and then a one by one convolution, max pooling, convolution, max pooling, all the way until we get to some very small resolution, in this case 4x4x6, and then we flatten it. Sort of ignore all of this. This is unnecessary tricks. But we sort of transfer this vector into a 32 numbers which represent that image. This is the smaller representation or the latent vector representation of that image that we would feed here. Okay. Well, this is half of the job because we sort of need to have another model which will be going from that resolution or that vector again back in here. And so in order to do that, we use the rest of this code. So we have a input of the second decoder model. We have the same size of the input as whatever this encoder was outputting, basically. We have a dense layer, some magic, or some additional layers which are not really necessary, but they sort of make the training easier. There is some normalization there. We reshape whatever we get here back into the 4x4x6 resolution, and then following almost like undoing this effect, so going from here to here, basically swapping between two types of layers, convolutions and then poolings. However, in this case, we are not downsampling, we are upsampling. So we are sort of rescaling it twice to sort of regain the original shape. So again, this is repeated convolution, upsampling, convolution, upsampling, convolution, upsampling, and then finally a convolution at the end. Okay. So this is then the decoder model, which goes from inputs to outputs. And then finally, we write a variational autoencoder model by basically wrapping around the image inputs by the encoder to get the latent vectors. We get the exact the z variable, and then wrap it around the decoder and say that these are the outputs, and we create a model from those inputs into these outputs, and that would be our variational autoencoder. So we just run this, and then we can plot. We can look at the summary of these two models, and even show the visualizations. So, let's see. I will hide this now. So in this case, we are looking at the encoder model, so something we have been seeing before. And then from this 32 vector, from the Z, we go back into the 28 by 28 original image resolution. Cool. What we also did at this moment, plot model, is that we saved the sort of alternative way how to visualize this. We saved a image representation of the same model, right? So this is the encoder, and then this would be the decoder. So encoder goes from an image all the way into a vector, and there is some like some stuff happening because of the of the variational autoencoder. So some loss which is calculated from these two parameters, and then the decoder which goes from that representation all the way back to the original resolution. Okay. I think we can also plot out or we can call the summary of the variational autoencoder and see what that gives us. It's a sort of compressed representation, so that will tell us that we have an encoder model which takes in this image and then plops out sort of different values, but one of them is the z coordinate, and then we convert that back into the image. We can also see the number of parameters, so this is sort of this is a guidance to how many convolutional layers should we use or not. So like me commenting some of them down and up, or having two convolutional layers per one stage would sort of mean that I'm getting more or less parameters at different in the decoder and the encoder. Okay, well, we created our models, and because these shapes were corresponding, so the input and output is the same, we can start feeding that in. So there is some amount of code which is measuring in the loss for the variational autoencoder. Basically, it's comparing the mean square error between inputs and outputs, and also some other functions which are coming from the variational autoencoder. So there is some sort of normalization aspect to the latent variable. So it's trying to have a good error on the distance between the images, but also have some good or have some restriction on the way how the z the latent variable has to be. So there are some losses that we don't have to really go into, but we will sort of just use them as a combination of these two aspects. So a difference between images and some internal like normalization. Okay, so we compiled our model now, and hopefully with all of this, we have the data in our training and testing datasets. We also have the model built, assigned with a loss, assigned with an optimizer, and now we can just start training it. So I think let's just train it for a while. I think something like 10 epochs should work relatively fast. So now it's training on the whole MNIST training dataset, which is 60,000 images, but they are really small resolution. So this should take not that much time. And we can see there is some loss which is going down, which is basically what we want. which means that the model is this loss is somehow represents the amount of detail that would be lost in between the image which is encoded and then the decoded image. Yeah. So sorry that this notebook is a little bit messier because it has all sorts of things that we don't have to sort of have that much intuition into. However, I think that including this, it makes the model slightly more usable. So if you come up with your own data here, you would be able to use it on some real dataset as well. Maybe more easily than just a demo, which would not be working anywhere else than with a MNIST dataset. Because honestly, that one is relatively easy. Okay, so history, we have saved history, and we will plot out how we went. Well, this went smoothly. I was training it for just 10 epochs. I think people can train it for 100 epochs and then get much better results, but I was training it just for the purpose of this demo to show on like a smaller scale sample. Okay, so we trained our model and we want to basically take it home or take it to our application somewhere, so we will just save it. I was fighting a little bit with the way how to save the model. Apparently there is some, these two functions, the save model and load model, is some tricks that are used to first kind of get the model architecture in first file and then get the weights into a second file. So without this, it went. I had some errors, but like basically using these functions, it should actually work anywhere. So we have a trained model at this moment. We have trained a variational autoencoder, but what to do with it basically? If you remember from the slides, there was some amount of details on the way how you can interact with variational autoencoders. I will try to explain some of them here as well in actual practical code. So we can load the model. I will not do it because we already have these two saved. But if you are transferring the saved file, the decoder MNIST and the decoder JSON, we would basically take these files, save them somewhere on your own PC, and then load them using this. Okay, and it should hopefully work if all the libraries versions are the same. Okay, so let's sort of start with the basics, how to actually use it. So X is one sample from the dataset. Right now, I'm just basically plotting out the sample. So we know that this is a 9, and this comes from the test 78 sample, and we can plot it. However, we can also encode it. So we can represent it as an array, use the encoder part of the model to convert this 28 by 28 by 1 into a, let's print it out, into a 1 by 32 vector. 1 means that we fed it with one sample here. So people often would feed a bunch of samples at once into a already trained model because it is faster. But right now we are just feeding one sample in, and so we get an array of z variables, and get the z0 would be the corresponding variable or corresponding vector for the first sample that we encoded. Cool, so this 9 is then encoded in the model by 32 latent variables as this. Which is honestly not really that nice, or like honestly not really that easy to understand. We don't really know what happens here, right? But this is some sort of latent representation of the image, sort of compression of all of that 28 by 28 numbers as compressed by just 32 numbers, which still is, what is it, 28 by 28. So we still are using like just a fraction of this whole amount of information. Cool. So we have the z latent variable here, and if we want to reconstruct it, we would basically just use the decoder model and predict the output sort of this z. So let's do it here. Oh yeah, okay, this is actually working nicely. I think I changed the model from before, so we can expect these two results, and they seem like quite nice. and this is a little bit messy code. I also showed you the same thing as we did now in 3 steps in just one single plot. And so let's see. Okay, so 9 would be reconstructed at 9, and this is the latent representation. 2 has a 1. Let's see. So 1 is also reconstructed. Nice. So all of these, there is some loss of detail, right? All of these seem to be working quite nicely. We can even like randomly print out 5 samples and just check them. And then, yeah, it seems to be working quite nicely. The MNIST dataset is easier as well than the other one I was trying. But yeah, so this is good so far. Okay. Well, I was explaining or talking about some autoencoder specific operations that we can sort of do, and some of it resulted in, or like talked about using these latent representations as an intermediate step, and then sort of moving around inside this space to generate new samples somewhere in between images. So this Z sample A encoded is us encoding a 1 into 32 numbers, and then encoding a 3 into, or sorry, a 0 image into 32 numbers again. So if we run it, we get basically two latent representations. I can even plot them out. So this one would be first one, this one would be the second one. Oh shit. Sorry, I think I need to show it. Huh. What's up? Okay, I will just copy paste the code then from this printout. Oh right, yeah. I think the problem is that the latent variable is yeah. Okay, I need to access the first sample. Right. Okay, cool. So now it's working. Good. Okay, so basically, this is a 1 and this is a 0 as encoded by this model. And what I want to do now is to have a linear interpolation between these two vectors. So have this function where we mix the first vector, so this thing, with this second vector, with this thing, and then sort of weigh it between these two by this number which goes from 0 to 1. Okay, so that's linear interpolation. Let's see what if the A is half. So let's get the half of these two vectors, and then use a decoder to predict for that mixed latent variable. Then we reshape it into image, and then should see the results. Okay, well, so this image apparently is somewhere in between 0 and 1. Well, this is sort of okay, but let's see this in more detail in sort of more fine-tuned translation. And so here we can see a smoother interpolation between 0 and 1. Okay, so this is nice. It's not super sort of user-friendly to use this sort of to just print them out like this, right? It's a bit messy. So one way how to go around it is we can use a Google Colab way of sort of encoding your code into a very nice user interface. So we would have these 3 parameters that are then basically running the same code that we were doing here, but just then plotting one single image. And so if we use that, we can have an interpolation between 0 and between these two samples. Let's randomly find some other ones, and then sort of see what we are dealing with. Okay, so it's an interpolation between 5 and 9. Okay, so yeah, so this is just a demo. Sort of we can just play around things. So between 8 and maybe 8 as well. Maybe we chose 2 8s. Oh no, it's a 3. Okay. Yeah. Well, so now we are basically getting the intermediate. I mean, the interpolations between 2 encoded samples, which with numbers is not as cool, I guess, but with other things like maybe faces, it would actually allow us to mix in identities of 2 people. So this was sort of one type of visualization of this, or usage of the variation autoencoders. Another one would be just to randomly sample any random latent and then see what that creates. And then basically get a lot of noise, because a lot of those numbers would be useless actually. Nice. All of what we create now is actually bad somehow. Interesting. Maybe it's due to the fact that the latent is very small, so let's like hack around with it, okay, a little bit. So these are some samples from inside the latent space of the model, but they don't correspond to any letter anymore. But they maybe have some shapes from inside the dataset. And so, oh, that one, yeah, this one is nice. So in theory, we are generating letters which don't exist now at this moment, even though we are doing it in very sort of brute approach, because we are just randomly going at some space of the hyperplane of that model of the 32-dimensional space and saying, hey, what's here? And what's here? What's here? What's here? And sort of forcing it to make something. We can also just create a bunch of zeros and then oversaturate it on one dimension. And so in theory, we are exploring what these dimensions mean. So the first dimension is a shape like this. The second dimension is a shape like this. The third dimension would be a shape like this. Well, and so from these, we are sort of trying to figure out what the model is, I guess, using to deconstruct construct a real sample. Because this is definitely not using it the way it should be. Because we are feeding it with some really high number, even though we should be basically getting values which correspond to this sort of distribution. Okay. There is some bonus visualization using GIFs. I know this worked with the other dataset, with the drawn glyphs. So I'm not sure if this will work here. I hope so. And oh, right. Let's create images, and then let's print them. It's empty for now. Cool. And then let's interpolate in that folder, and then let's see it. Okay, cool. So this is an interpolation between like 3x3 grid of samples, which were always 2 randomly sampled numbers, and then you're sort of interpolating between them. So this could be not 3x3, this could be more by more. If you edit this code, I think at this moment, and there's something like here you would have to change probably. Well, this is just a sort of bonus to sort of show what types of edits you can do with it and types of visualizations. Because honestly, like looking at it as this linear interpolation here is sort of awkward. So anything that can help bring in more intuition into it, something like this animation, is actually good. Okay, well, there are some bonus plots from the other dataset, which they look. It was more complicated dataset, so these look a little bit rubbish. And there were different versions of training it with different amount of epochs, for example. And I think the quality was getting better with larger amount of epochs. However, it's not that visible anyway. So this is just a bonus to like show all the results. Okay. If you would like to know a little bit more about all of this, well, I think at this moment you might be a little bit disappointed by the quality of these results, because this is a very low res dataset, and also we just trained it for like 5 or 10 epochs or something. And so I think mainly the resolution of the dataset is relatively small. So what you are creating is also relatively small. if you want to have your mind blown, basically, open up this Big Gun notebook. What they have is access to the Big Gun model, and that one is used to generate images of much higher resolution. However, so something like this. And so you would have similar sliders and similar sort of different categories that you can say, I want to create a container ship, and then move around with this and then create some samples which would correspond to this category. And so this is quite crazy, right? Like it's a data set which has a wig somewhere, a leopard somewhere, and a ship in its memory, sort of. So you can interpolate between a wig and a leopard, for example, somewhere as well, right? Between these samples, between a lizard and a baboon as well, and different types of dogs and stuff. So all of this and generate images which would correspond to a category of an image you uploaded it with. So all of this is a much better model than what we worked with. But the conceptual, like the functions that they would be calling behind the linear interpolation between some samples would actually be the same as what we had in this small demo here. So this is sort of like a, for example, I think if you are able to download a dataset, downsample it into 28 by 28, you can actually use this code here to train it on some demo data. However, a big gun like this, you probably wouldn't be able to train on your datasets. Or something like progressive gun, again, you would have to have a lot of compute, so not a Google Colab notebook, and also larger datasets. So it becomes all sorts of more problematic. But if you want to know more, you can check these samples as well. Okay, so I think basically this is the end of these two samples. I think maybe this one was quite long, and I will not look into the other dataset. However, you can sort of have a play around. You just swap the bit of code where you are loading the dataset at the start, and you can generate different samples from here. Okay, so I think basically it's the end for the practical session.